Hello dear friends, welcome to my channels. Today discussions is Feynman path integral part 1. Okay, so our topic is quantum field theory in path integral. Okay, so motivations, recall Schrodinger equations. I h bar del t state vector psi t equals to Hamiltonian acting with the state vector psi t. Okay, no problem. This is the equation of the Schrodinger equations. So friends, this equation is non-relativistic. This is non-relativistic non-relativistic path integral. Okay, problem, the goal is to find the timing positions, which means that given the state vector at some initial times. Okay, some initial times is given, problem given state vector ti and find okay, so final times at tf. Okay, so the goal is to find the timing positions, which means that given the state vector at some initial times and final times tf. Okay, tf. Now this is intrinsically non-relativistic because time is obviously is playing explicitly. Okay, time is non-relativistic. Why? Because time is explicit. Time is explicitly playing a special role. So note it, the time playing special role. Okay, what is the relativistic generalization? Generalization. Dirac had a proposal which we will be considering here in our discussion. So Dirac problem is formulated itself. Look for a formulation where both space of time are equal footing. Okay, so difference between classical mechanics and quantum mechanics. Okay, Okay, classical mechanics and quantum mechanics. So you need to know that classical mechanics are two-way. Classical mechanics are two portion Hamiltonian framework. Okay, Hamiltonian framework and Lagrangian framework. Okay, so we get two-way. One is Hamiltonian framework, another is Lagrangian framework. Okay, action is okay. We talked about a trajectory in an extended configuration space. The motion of the particle will be given by the some trajectory like that x, which you could describe as a function like like xi of t if you give some initial and final condition. Okay, so what is my trajectory? Let me draw. Okay, so this is the point, and x t. Okay, and this is x and this is t, x dash and t dash. Okay, so initial and final condition, say initial condition time ti and ti time ti and then x at tf. Okay, so this point is the x ti and this is the ti. Okay, this point, this is the ti. So and this is tf final and this is x tf. Okay, this is the total diagram. Okay, so what is the right trajectory through which the particle will move? Particle will move. Action functional is given by action. Okay, when you do this integral, you have to know to calculate the Lagrangian at a particular time. Okay, you will check. I have written one integrations and where I give also boundary conditions. Okay, so when you do this integral, you have to know to calculate the Lagrangian at a particular time. Then you integrate that function of time from t1 to t2, ti to tf. Okay, but in order to do so, you have to know what the function capital x of t is doing at ti and tf. So these are boundaries. So there are some boundary condition is that x at ti see some given value xi, and when I write with in square bracket, okay, you see s square bracket x. Okay, this is the square bracket. Square bracket means x does not refer to a real number, but x refer to an entire function of x of t. Okay, this is entire function, not real function. The in is an entire This is the entire path from the initial and the final point. From the initial point to the final point, so that the meaning of the square bracket of this notation action is not a function, rather it's a functional, because as input it is not taking a real number but the entire path. So function such that fx tends to fx such that r tends to r. Domain is real space of function. So function is this, and functional sx x square bracket x such that curly f tends to capital R. It is not a mapping from R to R. S is complicated space. This is complicated space to R. That more complicated is, let me call the curly f. Okay. So x is in the square bracket is not a real number, rather a path connecting to end points xi to xf. Space is infinite dimensional. Okay, suppose bracket x is a real number, which means x is a point in a space, which is a real line. Here, when x is in a garlic, it is in a square bracket, then x is a path, and then that x belongs to another space if the space of function s bracket of capital S bracket of x such that, okay, curly f tends to capital R, are just like we had this real line over here. We are trying to this is very easy for us to understand what this space is, but we are trying to have an understanding of what the space is curly f. Okay, so let us try to draw a cartoon this. Okay, okay, cartoon, that point is does not a real number but the entire path x with a square bracket. Okay, and this is the curly f infinite dimension. Okay, x with in square bracket corresponds to this entire path. What is the dimensionality of a space? Dimensionative space tells you how many independent direction you could move the original point. So in on the this piece on that a flat surface, we of course have two independent reaction because it is two dimensional space, but we are trying to imagine that it can be larger. For example, in case of three dimension, we draw a thing like this with respectively. This with perspective, we can imagine that it is a three-dimensional space. For four-dimensional, we cannot imagine, but we can be little more abstract to probe the questions. The more abstract question that you can ask is the if it is a number of ways, it is number of direction independent. Directions are the number of independent direction in which the more part this point can move. This point moving means this function is changing because this point represents this function on the path. So you could ask the question, in how many ways could I modify this path? And there are infinite number of ways because at each point you could make a change, and each point, and that will be independent change. As a result, you you will be to get these are the neighboring paths. So those neighboring paths, if you want to classify how they are different, they can differ from the original path in infinite number of ways, because at each point you have a degree of freedom of modifying the curve. Now we will discuss the classical mechanics. Okay, classical mechanics itself, how to reform classical mechanics in terms of action. Let us note down a few properties. So a few properties of action. Okay, now I will discuss few properties of action. Few properties of action. Number one, principle of least action. Minimization of Sx. Okay, I write minimization of Sx gives the classical solutions. And of course, when you extremize or minimize the action, that give one or few parts, because one for Sx generates canonical transformations. Okay, this is very important topic. Number two property is Sx generates canonical. Okay, canonical transformation. Sx generates canonical transformations that takes system from one climb to another. For example, harmonic oscillators. This is X and this is P. Okay. Okay, harmonic oscillators at space phase trajectories. This is the example. So this is X and P and this is P, and the classical trajectories are given by the ellipse. Okay, now the time here, so there are like path in the phase space. Okay, phase space. Okay, this is the phase space. Okay, spelling is PH because sometime it may be the problem may be accent. Okay, phase space. Okay, and example, harmonic oscillators. Okay, so harmonic of phase space. Okay, phase. So time is a internal parameters to these curves, to this ellipse. The time evolves, you are moving along that. Okay, initial condition can be any point on this trajectory. For example, this one, so the system starts to move from this initial condition onwards with time now, and therefore you know that harmonicals that are solid. Okay, and different trajectories are different. Now I discuss another important topic, that is Dirac proposals. Okay, this is my last topic, and after that I will stop my lectures and I will continue in my next video. You can, okay. So Dirac proposals. Suppose there is a particle which is moving from xi at ti to xf to tf. Okay, so xi to xi at ti and xf at tf. Okay, so that eigenstate of x, okay, eigenstate of x, if eigenstate of x at time ti with eigenvalue xi, overlap of the position against state except tf and xi ti somehow related to this object. Object is e I h bar s x. So friends, my first episode is complete. Now I will discuss in my next video. If possible, I will create another video for more details. Okay, this is the I h bar. H bar means Planck constant, I for imaginary number, and sx is the functional, s square bracket of x. So thanks for watching. I hope you enjoy my videos and my overall discussions. You will review my all discussion. Okay, review this.